Alright, hello. Today we're going to be talking about dot products and cross products. So first off, I just want to define our three-dimensional coordinate system. So our three-dimensional coordinate system will look something like this. And some books write it a little bit differently than other books, but physically it's really referring to the same object. Now in Matter and Interactions book that's written by Chabet and Sherwood, they define the x, y, and z axes like this. So that if we have some point here with coordinates A, B, C, what this is really referring to is simply how far out we're going in each of the respective axes. So we're going out A along the x-axis, B along the y-axis, and C kind of out of the screen like this. So that's the way that we'll define the three-dimensional coordinate system, and then we can talk about a vector starting at the origin and going to some point P like this. And so usually we'll write a vector as a letter with a little vector arrow hat above it. So now let's define what we're talking about when we mean dot product. So a dot product is a mathematical operation that takes two vectors and creates a scalar from those vectors. So let's give ourselves two vectors to play with here. So let's say, if we have some vector A that has coordinates A1, A2, and A3, and some vector B that's kind of defined the same way, B1, B2, B3, so that's the x, y, and z coordinates of B respectively, then the dot product of the two, vector A dotted with vector B, is simply going to be defined as the product of the first two coordinates, A1, B1, plus the product of the second two coordinates, A2, B2, plus the product of the last two coordinates, A3, B3. So this is the dot product. One other way that we can calculate the dot product is we can also say that A dotted with B is simply the magnitude of A, magnitude of vector A, times the magnitude of vector B, in other words the length of these two vectors multiplied by each other, times the cosine of the angle between the two vectors. So imagine here for a moment that you have two vectors. Suppose you have something like this, where maybe this is your vector A and this is your vector B, and suppose that the angle between them happens to be 90 degrees. Well, you can think about what cosine looks like. So you might remember cosine looks something like this. Bear with me here a little bit. So cosine of theta is something like this. So at 90 degrees, cosine of theta is 0. So your dot product in this case, if your angle theta is 90 degrees, then the dot product of two vectors, in other words, the dot product of two vectors perpendicular to each other, is going to be a big fat 0. So that is how we will talk about the dot product. Now, let's talk about it in a more physical setting, something using, an E&M example, for example. So suppose that you're starting off here, we have maybe a proton here, like this. And then suppose we have an electron, maybe out here, just to the right of the proton. And suppose we move this electron in kind of a semicircular arc to the other side of the proton. Okay, so all we've done is there's only one electron, but we've moved it to the other side of the proton. Now suppose that we want to find the work done here. So we think back to our mechanics class and we remember the way that we were defining work. So work is defined as the integral of the vector f dotted with the vector of dl. So here's the same dot product that we were talking about just a moment ago. And so we can use this little postulate that says, all right, the dot product is just simply going to be magnitude of f times the magnitude of dl times the cosine of the angle between the two vectors. So now it's a good idea to kind of think back to our physical situation and try to determine, all right, what exactly is going on with these two vectors. So I'm just going to kind of pick some random point in space here that the electron has to be at some point. And so we think about first the force that it's experiencing at that point. So the force is obviously going to be towards the proton, right? So here's our F. It's going to be wanting to go in this direction. But the actual direction that it's moving in, the dl, is actually tangent to the circle, something like this. And so what you notice now is that we have a nice situation where the two are perpendicular to each other. The two vectors are perpendicular to each other. So in other words, this angle theta right here is 90 degrees. And we just said a moment ago that if that angle theta is 90 degrees, then the dot product of the two vectors has to be 0. So this then just simply becomes 0 joules. So in other words, the work that it takes to bring the electron to the other side in the semicircular arc is 0 joules. Now that might seem a little counterintuitive to you. You might be thinking to yourself, like, wait a minute, how does that make any sense? But think about kind of an analogous situation in a mechanics class. So suppose you have, some sort of surface, a table, or something like that. It's not meant to be at an incline. Let me just try to create a nice horizontal surface like this. And now suppose you've got a block on this surface, or a brick, or something like this. And you want to figure out the work that it takes to move the block to the right. So your dl is going to be to the right, so simply the path that it's taking. But the force that the block is experiencing is straight down, force due to gravity. So you'll notice here is now the angle between dl and f is 90 degrees. And so the work that it takes to move that block across the horizontal surface is 0 joules. And this we know intuitively, and it's really the same situation that we're dealing with now in the E and M example. Those two vectors are always perpendicular to each other, and thus the dot product gives us a work of 0. Okay, so now let's talk about cross products. So you might remember just a moment ago when we were talking about dot products that we started with two vectors and we ended with a scalar, right? We started with, for example, we had two vectors in this case. We had an f and a dot dl. So there are two vectors, but we end with just the magnitude, just a number here, right? Because the dot product takes two vectors and kind of converts it into a scalar. I don't want to say converts, but we can get just a scalar value from this. Now, that's why this dot product is called the scalar product in some books. So now let's talk about the vector product. That's, again, this cross product. So in a cross product, what we're going to do is we'll start off with those same two vectors, and then we'll define A crossed with B. Now we want to come up with a single vector in this case. So the way that we do this is we take the determinant of the 3x3 matrix that's defined in this way. So here's your I, j, k unit vectors in the x, y, and z directions respectively. Now we're going to write out the components of vector A and the components of vector B, 1, B2, B3, just like this. And so what happens is, the way that we can calculate this is, if we're looking for example, the x component of this vector, so what we'll do is we'll take this ith component right here, this ith unit vector, and we sort of visually obstruct the row and the column that this unit vector is in. So we're only really left thinking about this 2x2 matrix in the lower right-hand corner. And so then what we can do is just simply take this product and subtract it from this product. So let me show you how that works in practice. So again, the ith unit vector, or in other words, the x component of this resultant vector is just simply going to be a2b3 minus a3b2. Now we do the same sort of thing for the j unit vector, except that this one's a little bit more complicated. We're going to have an extra negative sign out in front, so this is going to be negative a1b3 plus a3b1. And then finally, the z component, I'm just going on to the next line here because I've run out of space. This is simply going to be a1b2 minus a2b1. And so that is how we'll write the cross product. Now, what is really the physical significance of this cross product? Well, first thing that we notice is that it is a vector, and so that's kind of useful. If we were simply interested in the magnitude of this vector, we don't actually have to go through all this business. We can simply write that the magnitude of vector A crossed with vector B is simply the magnitude of vector A times the magnitude of vector B, and instead of the cosine like we had before, what we'll have is the sine of the angle between them. Okay, so think for a moment about what sine of theta versus theta looks like. You might want to draw this out. So here's my sine of theta versus theta. So it looks, something kind of like this. So what you'll notice here is that if theta equals 0, so in other words, if A and B are parallel to each other, so if theta equals 0, then the sine of theta equals 0, so the magnitude of the cross product of A and B also has to be 0. And that's something that's kind of useful. Now, one other thing that's sort of useful to talk about when we're dealing with these cross products is what the maximum is. Well, the maximum clearly happens when theta is pi over 2 or 90 degrees. So if theta equals 90 degrees, we have a maximum. A cross B is a maximum. It can't be any bigger than what it is when the angle between the two vectors is 90 degrees. Okay, great. Now I'm going to move this up so we can talk about kind of a physical example that uses this idea of a cross product. So this is one going back to kind of your mechanics days. So think for a moment here about this wrench. Here's the arm of the wrench, like this. And the wrench is, we're trying to turn some sort of screw or nut or something like that. Okay, and if you were a really smart wrench user, what you might want to do is you will kind of identify, okay, the arm of the wrench is going this way. I'm going to apply a force that's perfectly perpendicular to the arm, and that's all the way at the very end of the wrench. Now, the reason that you might intuitively want to do this is because you might be thinking to yourself, well, I know for sure that it's going to be easier that way. Well, let's talk about why mathematically it's easier. So what you're really doing is you're trying to maximize the amount of torque that's in that wrench. And remember, back in your mechanics class, that torque is defined as vector r crossed with vector f. So we've already drawn vector f in our diagram, but let's remember for a minute what this vector r is. So vector r is going to start at the axis of rotation, so it's going to start right here at this thing that we're turning. And it's going to end where the force is applied. And so here is my vector r. So vector r kind of runs the length of the wrench because our force is being applied at the very end of the wrench. And so now what we notice is we have a 90-degree angle between the force and the vector r. And so what we can say in this case is that we're going to get the most torque out of it, right? We already have this equation here. So we get maximum torque. We get a maximum torque when r and f are perpendicular. In other words, when the angle between them, when that angle theta is 90 degrees, because of this postulate right up here. We already talked about if theta is 90 degrees, then A cross B is a maximum. If you apply this force at any other angle, you will get slightly less torque out of it. Thanks for joining me for this Mathcast. See you soon.